Hello, this is section C of the 2007 PAT. So this is the long question at the end of the physics section. So I'm just going to do the one question in this video, and then the next one will wrap up the paper with the maths questions. So question 14, you should already be familiar with the mathematical treatment of an ideal pendulum. Well, if you're not, go and look at my video on it in the classical mechanics playlist, in which the pendulum bob is modelled as a point mass on the end of a rigid rod of negligible mass. Okay, in this problem you will consider the behaviour of more complex types of pendulum. You will be given all the information you need in the sections below. Right, so it's one of these ones where they're testing if we can use new information. For a general pendulum of any shape and size, the period P is given by this formula. Okay, that looks fairly complicated. So what are all these bits? Actually, it doesn't look too bad. It's just because of the subscript there. So G is the acceleration due to gravity. Fair enough. M is the total mass. So that's the rod and the bob at the end of it. LCM is the effective length of the pendulum, defined as the distance from the pivot to the center of mass. Okay. So if we've got our pendulum like that, then we're going to have a center of mass somewhere around here, say, and that is going to be our L center of mass. Okay. Where did I get to? I is the moment of inertia. Right, yes, again, something that I've covered in all my classical mechanics videos around the pivot point. So if you've looked at those, you'll have a bit of a head start here. For a point mass M at a distance r from the pivot, we've got I is mr squared. For a uniform rod of mass m and length r attached to the pivot at one end, then we've got a third of that for the moment of inertia. Right, for more complex objects, the total moment of inertia, yep, you can just add them up. We've done all that sort of stuff before. Identify LCM and I for an ideal pendulum of length L with a bob of mass m. So that's where the rod doesn't have any mass. We've just got a bob at the end. So the LCM, I'm sticking it up here because I think space is going to be at a premium in this. LCM is just going to be where are we? So yeah, center of mass, where it's just going to be all the masses in the bob. So it is going to be equal to L, which is the length of the pendulum, because there's no mass at all in the rod. So yeah, it's all going to be at the end. And what we got? And I. So I will just be equal to ml squared. That's good. And because we're taking that off of this formula here, where r is L, hence calculate its period. Right, so the period, well, we're hoping it's going to end up being 2 pi L over G, because we know that is our period of a standard pendulum. So we've got the 2 pi square root. So at the top, we've got ml squared, and we've got to divide by ml. So that leaves us with an L at the top and a G at the bottom. So as we'd expect for part A. So that's a nice reassuring starter. Repeat this calculation for a pendulum made from a uniform rod, mass m and length L. So in this case, we have no bob at the end. So let's stay on this margin, because I think we've got enough space to do this. So we know now that LCM is going to be the midpoint of the rod, L over 2, and that we know, well, we've been given it here is a third mr squared, so that's going to be a third ml squared. So we've got those, and now we have to plug that in again. We're going to get what we're going to get on all of this. So we've got our 2 pi again. We've got the square root at the top, so we're going to have a 3 at the bottom. That's never going to cancel with anything, and a g, that's not going to cancel with anything. We've got an ml squared divided by ml over 2, so that's going to leave us with 2l at the top. Okay, so everything's going swimmingly so far. I think they're going to, oh, here we go, they're ramping it up. 7 marks for this next bit. Consider the case of a real pendulum, bob of mass mb, treat as a point mass, attach to the pivot using a uniform rod of mass mr and length l. Find the period in this case. Okay, right, so we've got to add all of this up. Show that the result for a real pendulum reduces to the results of an ideal pendulum and a rod pendulum by taking appropriate limits. Okay, so we've got quite a bit of algebra we're going to have to do initially then. So we need to get the center of mass. So the center of mass is going to be, well, we need to do a weighted average of our two centers of mass that we've got. So we've got a center of mass of the bob we know is at LMB, and for the rod is at L over 2mr. So we're adding those together, and then we have to divide by the total mass in order to get the new center of mass. That's just sort of doing this weighted average. So that's going to be our LCM. That's going to be our new distance away, because we're saying, right, okay, if we've got some LMB which is going all the way to the end, and we've got some other L over 2 which is for the rod, where it depends on the relative masses of the bob and the rod as to how these things are going to combine, which is what we're doing here in this particular case. Right, so we know that the moments of inertia, we can just add them up. So we've got MBL squared plus a third MR, was it MR? Yeah, MRL squared. So that's our two moments of inertia added together, and now we have to put those two into the formula for the period. So this is going to be a right mess. 2 pi, I just hope I can actually squeeze this on, because this is going to be a lot of things to try and write on here. So what have we got? We got I at the top, so let's factorize that L squared. So we got L squared MB plus MR divided by 3. And then at the bottom we have got we've got our G and the new M, which is MB plus MR, and then we've got our L, which is this horrible looking thing. So we can factorize the L again. So L MB plus MR over 2. So I'm just about going to squeeze this on, divided by MB plus MR. Right, so we've got a lot of things that are going to cancel in all of this, which is really going to help matters, because that, well, let's change colour so I'm not cancelling things that I shouldn't be cancelling on all of this, so I can see what's going on. Right, that L is going to go with one of those L's. That bracket is going to go with that bracket. So we just need to deal with these 2s and 3s. So let's leave. So we've got the 2 pi. Let's put this 2 at the top and the other 3 at the bottom. So we'll have a 2L, but then we're going to have to remember to multiply through. So this MB is going to have to be 3 times as big in order to get that over the 3 that we can move to the bottom. And we're going to have a 2, I mean the 3 at the bottom, but a 2 on the MB at the bottom. So 2G, 2MB plus MR. Okay, I've done that a little quickly because I haven't got much space. You might want to do an intermediate step on that, but you can see I'm just dealing with these fractions of the half and the third here. So if you put them over a common denominator and then shift the 2 and the 3 around, then you'll end up at that step quite happily. So now there was something else in this question, but I can't remember what it is. So what have we done here? Show that find the period. Right, so we've done this bit, find the period. Show that the result for the real pendulum reduces to the ideal pendulum and the rod pendulum in appropriate limits. Right, so if we've got, so for the ideal pendulum, then we're saying that the mass of the rod is equal to 0. So if the mass of the rod is equal to 0, then this is gonna, the 2s and the 3s cancel, the MBs cancel, and then we get the period, I don't know, I'll put the arrow there. the period will go to 2 pi root L over G. Oh, that's a capital L. I'm just writing it as the standard way of writing down the pendulum formula. So that's fine. So that reduces to what we showed in part A. And if it is the rod pendulum, then the mass of the bob is equal to 0, which means that P is going to be going to, so mass of the bob goes down to 0. So we've got 2L, well, 2L over 3G, 2 pi times square root of 2L divided by 3G. So that is good because it matches with what we worked out up here in part B. So yeah, C has come out all fine and dandy. So yeah, happy with that. Right, for the remainder of this problem, you can consider an ideal pendulum for which you will calculate the effect of changing its environment. Right, okay. So we've still got the mass is just in the bob, but we do have a rod. It's not a string. Most substances expand with increasing temperature. So a metal rod will expand in length by a fraction alpha dt if the temperature is changed by this delta T. Right, and alpha is called the coefficient of linear thermal expansion. Right, we change the temperature. This rod, which has no mass, can somehow expand. Consider the effect of its expansion on a pendulum clock when a pendulum made from brass with that alpha. Okay. So what temperature change can this clock tolerate if it's to remain accurate for 1 second in 24 hours? Right, can I get another scroll? I can just about get another scroll on here. It gives me a lot of space to work in down the bottom. Right, so we've got all of this. So it's a fraction, they were saying. Right, so the length is increased by a fraction. And we want to get 1 second in 24 hours. Right, so 24 hours. Let's get how many seconds that is so 24 times 60 times 60. So 24 times 3,600. That is going to be 72,000 plus. So why am I deciding to do it in this long-winded way? Plus 18,000 minus 3,600. So that is going to be 86,400. You are allowed to use a calculator, but I just haven't actually turned mine on yet. So that's the number of seconds that we've got. So we want to do, if we do a fraction, our new period, so we've got 2 pi is root L over G for this one because we're doing the ideal pendulum. So we're going to have L, but this is a fraction increase. It expands the length by a fraction alpha delta T. So we're going to have L1 plus alpha delta T divided by G. That's our new period, the longer period. So if we divide that by 2 pi root L over G, that's our standard period, then that needs to be less than our 86401, adding on the extra second, divided by 86400. So we need to just keep that inside this change in fraction here. I'm saying I've got loads of space. I've now written massive writing on here. Right, so the 2 pi's, I'm going to go back into blue again to rearrange some of this. Let's go for the darker blue. Get rid of those 2 pi's. Right, so we're going to have to square everything. And then, well, the G's are going to cancel, the L's are going to cancel. So, yeah, we just need to start squaring stuff on all of this. And then things should drop out. Right, so, yeah, because we're just going to be left with the 1 plus alpha delta T squared. That's all we've got. So, yeah, that will cancel with that. That will cancel with that because they're all just factors. So we've now got the 1 plus alpha delta T has to be less than 86401 divided by 86400 all squared. So we take the 1 off either side, and then we divide by alpha. Alpha we know is, well, they've given it to us. So we plug all of that in, and that's going to give us, because alpha is this, 19 times 10 to the minus 6 Kelvin to the minus 1. Yeah, plug that in and we've got our delta T. This time I am going to have to turn the calculator on because I don't fancy doing any of that, because that looks pretty horrible. So delta T, I'm typing this in while I'm thinking. We've got on that, where was I? The 1 over alpha bit, type that in. What we got? 1.218. So we seem to be at two significant figures here. So let's say less than 1.2 Kelvin to two significant figures. Excuse me. Right. So yeah. So that's not bad. We've worked through. I think the key thing is it can be hard to spot that that's a fraction. So you might not know what to do with that alpha delta T, but if that is a fractional increase, then yeah, you're just adding it on to the existing length. So yeah, but you'd get a lot of sort of follow through marks on these if you had done it in some other way, providing you were, you know, at least getting the basic sense of then what you're trying to achieve. So we've just got part E left then. So repeat the calculation for a pendulum made from Invar alloy. Okay, whatever that is. With alpha equal to 1.2 times 10 to the minus 6. Right, so a much smaller alpha. So it's not going to expand by as much. So we should get a much higher delta T. All we have to do is go back. Fortunately, I've still got it sitting in the calculator. You can just leave all of that there and just change that value of alpha at the end to get another 2 marks. So for E, we've now got delta T has to be less than 19.3, so less than 19 Kelvin. So that is a big difference to two significant figures. So yeah, I like that question. I like it when they present you with new stuff and just see how you can cope with it, rather than bogging you down in really, oh, let's have some intricate, really fiddly algebra or something. The algebra in this isn't that bad. It's all on, well, can you assimilate this new knowledge? So I think those questions are really useful ones to practice on. So yeah, nice question.